In this video, I will show you how to find the resultant vector when you have two vectors that are acting together, even when the direction is not simply north or south or east or west. The key to my methodology is organization. Boom! I want you to use a graphic organizer like this to make your work more clear and easy to follow. So, a jet is flying with an airspeed of 480 miles per hour at a direction of north 82 degrees east. Because of the wind, the resultant speed of the plane is 518 miles per hour at a direction of north 79 degrees east. What are the speed and direction of the wind? So there are three vectors that we are dealing with. We have the velocity of the plane, so I'm just going to write plane right here. We have the velocity of the wind, so I'm going to write wind right here. And we have the resultant vector, so I'll just put resultant. All right, normally we're given the first two vectors and we are being asked to find the third. This problem is unusual because we're given the velocity of the plane and we're given the resultant velocity, and we're being asked to find the velocity of the wind. Now the first row is to record the magnitude and direction of each vector. The second row is to record the component form x comma y for each vector. So let's start by recording the magnitude and direction for each vector that we know. A plane is flying with an airspeed of 480 miles per hour. That's the magnitude, 480 miles per hour. Now the direction is north 82 degrees east. Now we can't use a direction like this in our calculation. We need to rewrite this as an angle measured counterclockwise from the east. So let's see, north 82 degrees east. That means start at north and turn 82 degrees towards the east. So that will put our vector right here, and this is the 82 degrees. All right, now what we need is the same direction, but we want to measure it from the positive x-axis. So these are complementary, so if this is 82 degrees, in order to add up to 90, this must be 8 degrees. And this is the angle that we actually need, the 8 degrees. Okay, let's do the same thing for the resultant vector that we're given. Okay, because of the wind, the plane is flying at 518 miles per hour. That's the magnitude, so 518 miles per hour. At a direction of north 79 degrees east. Okay, so north 79 degrees east. That means start at north and turn 79 degrees towards the east. So that vector would be here, and this angle is the 79 degrees. Now we can't use the 79 in our calculations because we need the angle measured counterclockwise from the east. So again, in order to add up to 90, this must be 11 degrees. So that's the angle that we will record on the table, 11 degrees. All right, now there's nothing we can do directly with the magnitude and direction. We can't add, we can't subtract. So what we need to do is convert these into component form. So you can convert the magnitude and direction into component form by doing r cosine theta for the horizontal component and r sine theta for the vertical component. So for the plane, r cosine theta means 480 cosine 8. R sine theta means 480 sine 8. So just use a calculator. So the horizontal component is 475.33 and the vertical component is 66.80. And we record that on the chart right here. Let's go ahead over to the resultant and do the same thing. R cosine theta is going to be 518 cosine 11. R sine theta will be 518 sine 11. Calculator. So the horizontal component is 508.48 and the vertical component is 98.84. And we'll record that here. So we have the resultant in component form and we have the plane. So our job now is to find the wind. Now remember that normally we'd go like this. The plane plus the wind would equal the resultant. All right, but this time we're trying to find the wind. So subtracting the plane from both sides, we should be able to find the wind by doing the resultant minus the plane. So that's what we're going to do to find the component form for the wind. We're going to take the resultant and we're going to subtract the plane. So I'm about to do 508.48 minus 475.33. That gives me 33.15 for the horizontal component of the wind velocity. Now I'm about to do 98.84 minus 66.80. So now we have a vector for the wind. This represents the velocity of the wind. However, we need to convert this back into a magnitude and direction, similar to what we got for the plane. We have the magnitude and direction, and for the resultant, we have the magnitude and direction. Okay, so let's do that. If I want to find the magnitude, I can just do like this. Let's see, magnitude. And direction. So for the magnitude, I can simply use the magnitude formula. So I will do 33.15 squared and then 32.04 squared and use a calculator. So that's 46.10. That is the magnitude of the wind, or wind speed. 46.1. So let's go ahead and record that on the table. So 46.10 miles per hour. Okay, now we just need the direction. So for the direction, looking at the fact that we have a positive horizontal component and a positive vertical component, that means that we are to the right and up on this chart, east and north. So we're in the first quadrant. So let us draw ourselves the vector in the first quadrant. Now imagine the horizontal and vertical components. So here's my horizontal component, and here's my vertical component. So that's why the 33.15 will go here, and the vertical component of 32.04 will go here. So I can find this angle theta by using the tangent function. So theta will equal the inverse tangent of 32.04 over 33.15. So just put that in your calculator. That's 44.02 degrees for the direction. Okay, however, we have to be careful. For the final answer, you have to make sure that any direction is written in the same format that you were given in the original problem. So they didn't just give me an angle measured from the positive x-axis, they gave me things like north 82 degrees east, north 79 degrees east. So I need to rewrite this using that format. So here comes the true answer. The magnitude is not going to change, so the wind speed is still 46.10 miles per hour. So I'm going to keep that, but I need to change this. Okay, so I could think of this direction as starting from the east, turn 44.02 degrees towards the north. So again, starting from the east, turn 44.02 degrees towards the north. All right, so instead of just writing that, I'm going to write east 44.02 degrees north. So this is the final answer. Boom, there it is. If you like it, then you should have put a box on it. Always box your final answer. Let's do one more problem on this video. Nick's crew team rows due west across a river at a rate of 7 kilometers per hour. The river is heading west 15 degrees south at a rate of 2.3 kilometers per hour. Find the resultant speed and direction of Nick's boat. Organization is the key, y'all. Boom! Use the chart. Seems to me that we have two vectors that we are dealing with. We have the velocity of the boat, okay, the velocity that we would have if there was no current, which is the other vector, is the river current. And then, of course, the net result of those two acting together is called the resultant. In the first row, we will faithfully record the magnitude and direction of each vector. In the second row, we will put the component form x comma y of each vector. So the boat moving at a rate of 7 kilometers per hour, that's the magnitude then, 7, and I'll just put kph, all right, for kilometers per hour. Now, the boat is moving due west. So if we're talking about due west, that would be like this. Okay, that's due west. As far as an angle measured from the positive x-axis, that would be this, which is 180 degrees. So that's the angle I'm going to record on my chart, 180 degrees. Now, how about the current? The river is heading west 15 degrees south at a rate of 2.3 kilometers per hour. The 2.3 kilometers per hour is the magnitude. Now let's talk about this direction. West 15 degrees south. West 15 degrees south means start at west and turn 15 degrees towards the south. So that will put our vector here, and this is 15 degrees. So for the chart, we need an angle that is measured counterclockwise from the positive x-axis. We need an angle that's measured from here, like this. All right, we call it theta, and in this case, theta should be 180 plus the extra 15 degrees. Okay, so theta is going to be 195 degrees, and that's what goes on the chart, 195 degrees. Now, there's no way to directly add these. When you have the magnitude and direction, you can't just add them up and get the magnitude and direction of the resultant vector. Instead, we need to convert these to component form so that we can add them together. All right, component form. We've got the horizontal component, the vertical component. Normally, I do r cosine theta, r sine theta. But not when you have a horizontal or a vertical vector. That would be silly. So this horizontal vector has no vertical component at all. So that means the entire 7 kilometers per hour is a horizontal component. So I'm going to put -7 here because it is going to the left. It's going to the west. That's the negative direction. I'm going to put 0 for the vertical component because there is no vertical component. It's all horizontal. So that's it. No calculator, no nothing. Now, on the other hand, when I want to convert the current into component form, it's not horizontal or vertical. So I need to remember that anytime I want the horizontal component, I do r cosine theta, and the vertical component is r sine theta. So that's what I'm about to do now. So r cosine theta, in this case, will be 2.3 cosine 195. And r sine theta is 2.3 sine 195. So use a calculator. So the horizontal component is -2.22, and the vertical component is negative, well, this is going to round up, so 59 becomes 60, so this will be -0.60. And we'll just record that on the chart like this. Now that we have both vectors in component form, in order to find the resultant, all I have to do is add. So just add this vector and this vector together, adding the corresponding components together. So that gives you -9.22, -0.60. So this is the resultant vector. Only thing is, now we need to convert it to a magnitude and direction, just like we had with the other two vectors. So let's see, magnitude and direction. Let's start with magnitude. All right, if I want to find the magnitude, I can simply use the magnitude formula. So I will do -9.22 squared plus -0.60 squared, and I'll do the square root of all that in my calculator. That's 9.24, and in context, that means the magnitude is 9.24 kilometers per hour. All right, that will be the speed of the boat once you take into account the effect of the current as well. So that's the magnitude. Now we need the direction. Let's see. So for the direction, we have a negative horizontal component and a negative vertical component. That means this vector is going to the left and down. So we're definitely dealing with the third quadrant. So draw a third quadrant vector. And then go ahead and break that apart into its vertical and horizontal components. So my horizontal component is the negative 9.22, and the vertical component is the negative 0.60. We can use this to find the, well, you know what, I should call this R, because this is about to be the reference angle. Okay, we can use this to find the reference angle R by doing tangent, because the tangent of R should equal 0.60 over 9.22. Notice I'm ignoring the negative signs because I really just want the positive value of angle R. So ignore the negative signs. Now the measure of this reference angle should equal the inverse tangent of the fraction. And put that in a calculator. So the reference angle is 3.72 degrees. Now we can find an angle measured from the positive x-axis. All right, we call this angle theta. And theta would be 180 degrees plus the extra reference angle. So theta should be 183.72 degrees. So that is one way of describing the direction of the resultant vector, 183.72. However, this is not going to be our final answer. Because of this direction, we have to be careful. Our final answer, we should give the direction using the same format that they use to give us the direction. So look at this direction, for example, west 15 degrees south. We need to use this type of format for the direction of our final answer. Okay, so I'm going to rewrite this answer, making that change to the direction. The magnitude's not going to change, so I'm going to write 9.24 kilometers per hour. I'm just going to write that again. Now let's take a second look at the direction. So if I want to still use the reference angle 3.72, I could think of this as starting at west and then turning 3.72 degrees towards the south. All right, again, I could think of this as starting at west and turning the 3.72 degrees towards the south. So this is the way that we need to write the direction in our final answer. So west 3.72 degrees south. Go ahead and put a nice box around it because this is the final answer.